this will be the last KCS talk for this semester, right? People are coming, but we need to start. So the speaker for today is Dr. Shixiong, all right? The title of his talk is Building Software-Based Cellular Networks, all right? Lessons for Evolving to 6G. This is the first ever work that try to use software to run network services. I would like to emphasize this part, the first ever work in this direction. So it's going to be very interesting, right? So let's welcome today's speaker, Dr. Chi. Right?
Okay, so thanks for introduction, my friend. And this work is about the lessons we learned for developing a softwarized cellular network. And I want to show some of the lessons we learned for how we should evolve to the next generation of the.
Can you put the mic closer?
Yeah. So
turn the volume.
I can put it here. Okay. So basically, and how we should evolve to the next generation of the cellular networks. And this is a joint work together with many others from UC Riverside and also from national Young universities, especially with my advisor, Professor Krishna, and also the lead at the NYCU, Professor Shixiong, and many of their students. So to begin with, I believe most of you are using the cellular networks every day using mobile phones, and you probably already heard about the terminologies of mobile networks, and 2G, 3G, 4G, and the 5G you are using right now. And what is the cellular networks? So the cellular network is basically a communication systems that allows the mobile devices, and I use the terminology, the user equipment to describe these mobile devices, and to let them connect to the backend internet services so that you can make the calls or send and receive data with the different services in the cloud. And how can the user equipment connect to the internet services over the wireless network? And when you drive your car on the road, you may find these different devices look like this. And this is the outdoor cellular towers. And this tower will basically broadcast the wireless signals. And if you use the equipment within the coverage area of this tower, then you can get access from this tower to the backend internet services. And especially these different towers, they have a specific coverage areas. And for example, this outdoor tower, its coverage range can be up to 8,000 feet. And if you are within a stadium and you look at the ceiling, you may find something like this, which is called an indoor cellular site. It is more power efficient compared to an outdoor cellular tower, but its coverage area is also smaller. It's usually within a range of 300 to 800 feet. And if you are sitting within a room, like in your lab, you may find something like this, and we call it a dome antenna. So it is even more power efficient than the indoor cellular site that is attached to the ceiling, but its coverage area is much more smaller, usually around 100 feet. And with this different outdoor cellular tower and indoor cellular site, they are basically organized as cellular networks that can provide the wireless network or wireless connections to our user equipment, and our user equipment can use the wireless network to access the backend internet services. And right now, if I ask you, what is a cellular network? I don't know whether you just consider the cellular network as a group of these different radio sites, but of course it's not. There's actually something seated between the backend internet services, which is called the core network. This part, I believe you never heard any of this before. And actually, the core network exists since the second generation of our cellular networks, or 2G. And it is deployed and used since the early 1990s. And the question you may have is, why do we need a core network? We just need a wireless connection, right? But if you look at the radio network or the wireless network, it is actually a very large-scale distributed systems that provide the end wireless connections to user devices. But how can we manage is such a large-scale distributed network, we need a centralized controllers. And the core network essentially plays that role of the centralized controllers to control and manage the end or the end user equipment by doing the service usage and billing and also user session management. And what is the user sessions? So essentially before your user equipment can connect to the backend internet services over the Cellular network, they need to establish something like a connections. And here, in the context of Cellular network, we call this connection the user sessions. And only after you are set up your user sessions in the core network or the Cellular network, you will get authorized, register your device into the network, and then you can access the backend internet services through the Cellular networks. And in that sense, the core network essentially will act as a gateway that sits between the radio network and the internet services to offer backend connectivities to the user devices. And next, I will discuss several evolutions of the Cellular networks in different aspects. And the first important evolution is basically the movement from the purpose-built appliance to the softwarized and the virtualized network functions. And here, this figure just shows a blade system for the core network that is built by the Ericssons. You can see it is very huge and very complex. And if the Cellular operators, let's say the Verizon or AT&T, they want to add some new features to their core network by improve their network functions, they need to ask Ericssons to develop some new hardware for them. And that will basically make the development period to be much longer and also increase their cost. So that's why many of these Cellular operators, like AT&T, Verizon, they try to jump into a softwarized network functions, basically by convert this hardware into a software, so that they can directly use any of these company servers that is in the cloud and directly deploy these authorized and virtualized functions, which is more flexible compared to the purpose-built appliance. And that is the first movement. And the second movement in the evolution of the Cellular core is basically the use of the microservices. I don't know whether you heard this before, but it's very popular in the software engineering communities, and those are people, they use the microservice paradigm to build very complex cloud applications. And just taking this online beauty application from Google as example, what you can see is that every single piece of it is actually deployed as a single purpose microservices that are loosely coupled with each others. And the benefit is very clear. Basically, for each of these microservices, they can be deployed independently, and they are very easy to scale out. And nowadays, this approach has also been used by the Cellular network communities to develop softwarized network functions, as you can see from the shift from the 4G core network to the 5G core network. And the significant difference you can see here is that in the 4G LTE EPC, or the core network, the network functions basically is deployed as a monolithic functions, but in the 5G, they are decoupled into more functions. For example, this mobility management functions in the 4G LTE core is basically decoupled into the AMF, the access and management functions, and also the AUSF, the authentication functions, and the SMF, the session management functions. It is decoupled into three functions, essentially. And for the HSS, which is the database that is used to store the user data, it is decoupled to the UDM and the UDR in the 5G architectures. So you can see that the 5G core, especially its control plane, it becomes more decoupled by using these microservice-based architectures. And this will give us lots of flexibilities. Basically, we can develop these functions as decoupled softwarized microservices, and we can scale up them or scale down them independently to reduce our operational cost. And this is the main intention why these different Cellular providers, they try to use the microservice and also the softwarizations into their deployment of the core network. So now let's take a closer look at the 5G core. And basically, the essential thing I want to introduce here is that the 5G core use a control and user plan separation philosophy. And sometimes we call the user plan as data plan. I will use these different terminologies interchangeably in my talk. And if you look at the data plan, or the data plan of the 5G core, the UPF or the user plan functions is the only functions we have. And its responsibility is to forward the data or the data traffic between the radio access network and the backend data network or the internet. But within the control plane, we can see many control plane functions because of the adoption of the softwareization and microservice-based paradigm. And these different decoupled control plane functions, they will collaboratively work together to handle the state associated with the user sessions, for example, the session establishment, the mobility event handling, and also the policy adjustment. And their responsibility, basically, or the eventual outcomes of their collaboration is to set up the connectivities between the mobile devices and the internet in the user plane. But the problem is that the existing 3GPP SPI, the 3GPP, they enforce us to use a service-based interface for the communication between these different control plane NAVs. And 3GPP is basically the third generation partnership project, which is a group of standard organizations that work together to develop the protocols for the mobile data communications.
Can you explain the difference between control plane and the data plane?
So the control plane is basically do some control activities, for example, setting up the connections between the mobile devices and the backend internet services. And the user plane is just used to forward the data between these endpoints.
So data plane is also called the user plane?
Yes. Basically, I use the user plane, data plane interchangeably.
So those two terms?
Yeah, they're same thing, actually.
The same thing, all right.
Yeah. Sometimes people, they like to call the user plane, but sometimes they like to call that data plane, but they are the same thing, actually.
All right.
So I just talk about the evolution of the neural core networks, but there are different aspects I want to touch, especially the evolution in other aspects. And the next one is the emerging use cases in the neural networks. Especially all of these emerging applications, they want to depend on the ubiquitous connectivities that can be provided by our wireless neural networks. And typical example is the portable AR, VR, and also self-driving cars, because it's not feasible to use a provide wired connectivities for these devices or applications to connect to the backend internet services. So they have to rely on the neural network for the wireless network access. But they have a common requirement, which is the low latency and high throughput network access in the user plane or the data plane. And the last aspect of this evolution is on the radio side, or the radio network side. Basically, in the 4G RAN, we use the microwave, but in the 5G RAN, you may heard that we already switched to the millimeter wave. And why do we want to use the millimeter wave to replace the microwave? It's because millimeter wave can give us much higher bandwidth and also lower latencies. But the deficiency of the millimeter wave is that it has smaller coverage. As you can see from this transition here, 4G RAN's microwave can provide a broader coverage area for each cellular site. But in the 5G RAN, the millimeter wave, for its limited coverage, we need to deploy more cell sites to provide enough coverage for our mobile devices. So here's the takeaways I want to summarize on the evolution of these different aspects of the cellular networks. So we see that in the cellular core network, especially in the control plane part, the operators, they try to use the softwareization and the microservice-based paradigm to lower their operational cost. And in the radio access network part, they are trying to switch to the millimeter wave, which has smaller coverage, but in the meantime, it can give them much better bandwidth and low latency. And all of this purpose is to serve or fulfill the requirement of the future emerging applications which exactly demand the low latency and high throughput network access in the user planes. But actually, there's a disharmony between the evolution of these three different aspects. And the reason is because we often overlook the impact of the control plane on the user planes. And here you may have a gap of understanding why the control plane can have a negative impact on the user plane, and I will explain that. So why does the control plane matters? And to answer these questions, we basically need to understand the penalties of doing the softwareization and also use these microservices in developing our cellular core control planes. And I will explain this penalty in three different aspects. The first aspect is the system implementation of the Cellular core control plans, which is because of the use of the softwareizations and microservice itself. And the second is because of the complex protocol designs in the Cellular core control plans, which can magnify the deficiencies of our system implementations in the control plans. And the last one, although it is not from the core network itself, but it has some external factors, mainly caused by the radio access network, which will also magnify the deficiencies in the system implementations. And I will walk through or analyze the reasons of these each one by one. So for first, why the system implementations of our Cellular core network can give us the penalties which we don't want to have. If you look at our control plan network functions, they are actually loosely coupled each other as microservices. And especially these different microservices or network functions, they need to collaboratively work together to complete a certain control plan tasks. And they need to depend on the networking by using the 3GPP defined SPI to send messages with each others. And here I will use the example of these UE authentications, which is part of the entire UE registration procedures. And why it is important, because every time before your phone get registered into the core network or the Cellular network, your phone must be authorized first by the core network. And you can see that this diagram basically describes the message exchange between different control plan network functions. And you can see just for a simple UE authentication task, there are many messages that exchanged between different control plan functions. But given the fact that the control plan navs, they communicate over the 3GPP SPI, which is actually use the kernel-based HTTP REST APIs. This will increase the cost for the interactions between different control plan network functions, or basically increase the control plan latencies to complete a certain task. And this means that we need to speed up the nav communications in the control plan to minimize this cost or penalty. And for the second penalty, it's because of the complex protocol designs. And here, I will use another two control plan event to explain the complexity of the control plan protocols. On the previous slides, I already show the complexity of the UE authentications. For just a simple task, you incur many messages between different control plan functions. And here, for this handover mobility events, it even takes more communicating messages between the control plan functions. And when the handover mobility event will happen, it's basically when your mobile phones switch from a coverage area of one cell site to another one, then you need to switch your user state between these different Cellular sites. And because the state transition is triggered, then the core network needs to coordinate the state between these different cell sites and move your user data from one to the others. And that is the key idea of the handover mobility event. But just for this mobility event, you can see that it incurs around 25 messages just between the three different network functions in the core network, the AMF, the SMF, and the UPF. And another example is basically the idle to active transitions, or the paging event. And why do we need this event? It's basically to save the power of your mobile devices. If your mobile devices is idle for a certain while, then the core network will basically notify your mobile phone to disconnect it from the network to help you save power. But let's say if there's any messages that is coming to your phone, then by this time, the Cellular core network will send a notification again to your phone to tell you you should wake up and receive the data. And this will trigger the idle to active transition, or the paging event in the core network. And they will run these complex protocols to complete this task, which incurs more than 15 messages. But again, I believe you haven't understand why the control plan can impact the data plan. But the key reason is that is this sentence. Basically, during the completion of the control plan event, all the data packets in the user plans, they need to be buffered at the core network during these times. And if the control plan event completion time is longer, then that means there will be more time spent by the data network in the core network to be buffered. and impact the user experience because the data buffer is buffered in the core network and it's not consumed by either the internet services or the mobile devices. And what we need to do is we want the change in the control plane to be quick for complete these complex protocols so that the packet in the data planes, they can be forwarded without additional buffering delays. And that is the key takeaways of this second penalties. And for the third penalties, which is caused by the external factors from the radio access networks. And as I said earlier, the 5G RAN is jumping to the millimeter wave, and this will cause a smaller cells or smaller coverage of each cells. And what is the penalty of that? Basically, if you compare what we see when we have the 4G LTE microwave and the 5G millimeter wave, what we will see is that because of the smaller coverage of each cell, we will see more handover events if you just move the same distance from one side to the other one. And what does it mean? It means that there will be more work for the core network to be done to handle these different control plane tasks. And again, if we want, although we cannot totally avoid these penalties, but we can try to minimize penalty by speed up our control plane. And that is the key takeaways for the third penalties. So here, we already know the importance of the control planes, and we can no longer overlook its impact of the control plane on the user planes. And the next question is how can we improve it? By basically speed up these operations in the control planes. And I want to discuss two aspects. The first is how we can improve the systems to speed up control plane operations. And the second is how we can optimize the protocol designs to reduce this overhead. But due to time limitation, I think I can only cover the first one. And for the second one, I will briefly touch upon. And if you have any questions, you can ask me offline. So let's take a closer look at the problem of the system implementations. Basically, we know that the control plane MNFs, because they are decoupled, they need to use the 3GPP SPI to communicate with each others. And this is common for all of these existing 5G core network solutions right now, like the free 5GC, the OAI core, the Open 5GS, and the Aether core. And all of them, they depend on the kernel-based HTTP REST APIs. But the kernel-based HTTP REST API is very slow because of the overhead introduced along the data path. And here shows when we deploy a network functions as our containers, and all the overhead from one containers to the other containers when they send a message is introduced along the data bus, including the data copies, the protocol processing, context switches, interrupt, serialization, and deserializations. And all of this will be translated into the CPU cycles and the memory bandwidth. And that will increase your latencies and basically reduce the performance. And what we can do to replace this kernel-based networking is to use a concept called shared memory processing. And this figure shows the difference between the kernel-based networking and the shared memory processing. And the key idea of the shared memory processing is basically we put the data into a shared memory pool that is accessible by both the source and destination functions. And instead of relies on the kernel to pass the data between the source and destinations, they simply pass a reference, which is the data descriptors that point to the data in the shared memory between the containers to enable the communications so that we can avoid all of this overhead because of the use of the kernel-based networking. And the shared memory processing has been widely used to enable high-performance networking in the context of network function virtualizations. And the typical and also one of the most popular platforms that people use to build the shared memory processing for NFV is the OpenNetVM. And this figure shows the basic architectures of the OpenNetVM. And there are several key innovations that can make the performance, the networking to be between the containers to be very high performance. The first is that in the user space, there is an NF manager component that use the pooling to move the data between the NIC and the user space shared memory pool so that we can avoid that interrupt-driven packet processing overhead and totally bypass the kernels, and we won't incur any overhead caused by the kernel. And second is that the OpenNetVM provide a log-free operations, basically that each network functions to have its own ring pairs to exchange the descriptors, which is the key to enable the shared memories. And by using shared memories, we can totally avoid any of this overhead we saw earlier and just enable the zero-copy data transfers between the NFs to improve the performance. And overall, the throughput of the OpenNetVM can achieve multiple tens of gigabits per second and just get a latency with less than tens of microseconds. But can we use the shared memory processing in the 5G control plan functions directly? Of course not. And there are several limitations of the existing shared memory framework for NFV. And these limitations will cause us cannot directly apply the shared memory to speed up the control plan operations in the 5G core. And the first limitation is the mismatch between the asynchronous I/O and the synchronous I/O. And essentially, the shared memory processing in the existing frameworks, they only support the asynchronous I/O. But on the other hand, the 3GPP SPI, it requires the synchronous I/O operations. And why this matters? If you look at these examples, so when the caller either use the asynchronous I/O or the synchronous I/O to send a message to the callee in the other network functions, they will use the sender call to send the data, and on the other hand, the callee functions will use the receive call to receive the data. In this stage, they are the same, but the difference is that for the synchronous I/O, the caller or the caller will basically expect a response from the callee, and it has to be blocked to wait for the response to return before it proceeds to do other tasks. But for the asynchronous I/O, it will not. After it sends out the data to the callee, the caller thread will directly proceed without expecting anything. So this mismatch will cause us cannot directly use the asynchronous shared memory I/O to establish the synchronous 3GPP SPI. And the second limitation is because of the shared memory I/O essentially is stateless, because most of the shared memory framework that is built for NFV, they focus on the layer 2 and layer 3 packet processings. And they don't have a support for stateful I/O processings, which makes them unable to dispatch messages to the user thread to different user threads in the network functions. And this will also cause them unable to scale up to concurrent user sessions, which is very important because in the 5G core functions, we are very common to use the multi-threading to support concurrent user session handling. And in our early version of our 5G core, we only support 2 concurrent user sessions because of these issues. And that's why we have to improve that. And the last limitation is basically because of the programming language incompatibilities. And many of these 5G core platforms, they use the high-level programming languages for developing the control plan NAVs because this can reduce their development effort. And you can find this to be commonly exist in different 5G platforms like FreeFireGC, the Aether SD cores. But on the other side, the NFV and high-performance packet I/O frameworks, they often use low-level programming languages, such as C, for the purpose of high performance. But using C to develop complex layer 7 microservices will increase their development complexities. Although we can directly port the existing 5G cores to use the high-performance NFV framework, but that will require massive code changes. That means tens of development work, which we want to avoid. So that's why we developed this framework called Layer 2 5G Plus, which is an improved 3GPP compliant 5G core for low latency control plan operations. So the Layer 2 5G Plus basically is developed on top of the combination of the OpenNetVM and also the FreeFireGC. By using the zero-copy packet delivery and also log-free producer consumer rings, the Layer 2 5G Plus can benefit from the high-performance shared memory processings. But because of the limitations that is inherently existed in the OpenNetVM, we have to do some improvement, basically having a synchronous I/O over shared memory instead of asynchronous I/O, and also add support for the concurrent sessions, and also resolve these language incompatibilities. And for this purpose, we developed a I/O framework called XIO, which is high-performance unified I/O interface we especially developed for this 5G framework. And this figure basically shows the entire architectures of the Layer 2 5G Plus and how to use XIO to resolve to overcome the difficulties for directly using OpenNetVM. So at the bottom, what we can see is that we developed an I/O stack that using shared memory called XIO stack. The purpose for having this I/O stack is to use the shared memory to retain the high performance networking in the control planes. But the problem is that the XIO stack only expose, or the shared memory I/O stack only expose the asynchronous I/O and is not compatible with the upper layer applications or the network functions. And to resolve that conflicts, we basically introduce an XIO API libs. And that is the key component to convert or interface the upper layer network functions that depends on the synchronous I/O with the underlying interface with the underlying asynchronous I/O shared memory I/O stacks. And by doing this, we can make sure our implementation can be fully 3GPP appliant. That is the key for other people to use our framework. And to support the concurrent connection management, we basically introduce a user session tables by turning the stateless I/O stack into a stateful one, so that we can scale up to a number of concurrent user sessions. And for the cross-language support, we basically use the SIGO interface in Golang to interface the upper layer Go-based implementations under underlying C-based I/O stacks, so that we can reduce our porting effort and can directly use the unchanged Golang navs from the free file GCs. So we don't need to develop our network functions from scratch. So next, I will basically go through the details of this each component one by one. The first is the high-performance XIO stack, which is built on top of OpenNetVM. So to enable the shared memory processing, what we need to have is to have a shared memory pool that is accessible by the different applications. And the key idea here is to use a memory map. Basically, you can map the memory of one applications into the address space of the memory in other applications to make sure they have the same view of that shared memory pool. And the key to enable the zero-copy delivery is to pass the descriptors instead of real data. And for that purpose, we basically use the log-free descriptor exchange from the OpenNetVM to enable the descriptor exchange between different navs. And as you can see here, so for each network functions, they have a pair of rings for the receive and transmit of the packet descriptors. And to make sure the access to these rings, they are log-free, the most important component we introduce is the centralized NF manager that we deployed on each node. And the NF will only share the rings with the NF managers. They will not share these rings with any others. And because only the NF managers or the application itself has access to a ring, so we can construct a single producer, single consumer patterns, and thereby we can avoid any log acquires when either the applications or the NF managers have access to these rings.
Any particular reason for using a stack in your XIO?
It's basically to directly leverage the shared memory processing from these mainstream NFV platforms, so that we can retain a high-performance data plans to transmit the control plan messages between different network functions.
A stack can achieve that goal or that purpose?
Basically, the I/O stack is for high-performance message deliveries between different functions. And each function will have their own I/O stacks to handle the message delivery over the shared memory. And in the I/O stack, in the XIO stack, we basically expose several zero-copy I/O primitives, including the malloc and also the TX and RX, which is the two primitives we use to do the shared memory processing. But because of all of these I/O primitives, they are returned in an asynchronous way, and they are basically developed in C. So they will cause some conflicts with upper layer Golang-based implementations. And for that purpose, we have these XIO API libs.
Also, you mentioned Golang, that term several times. Did you ever define that thing, Golang?
The Golang is basically a programming languages that lots of people use it to do the programming and development of the software, especially for the cloud-native microservices.
So it's just a programming language?
Yes, it's a programming language, and it's very easy to use. And to resolve the conflicts between the upper layer Golang-based 5G NFs and the underlay C-based XIO stack, and for the mismatch between the asynchronous I/O and the synchronous I/O, we basically introduce API libs called XIO API lib. And the XIO API libs take a typical layer design, as you can see. At the bottom, we introduce, the bottom layer is basically a POSIX-like socket APIs, which provide equivalent Golang-style socket interfaces like the read and write, which we can use to receive the data, receive or send the data. And also the listen, accept, and dial, which we can use to establish the connections between different network functions. And on top of the socket API, we basically integrate the Golang's HTTP REST APIs into that, and without any changes. And further, by going further, we can develop the 3GPP API by just reusing the HTTP REST APIs that we developed in our Golang-based API libs. And to resolve the programming language incompatibilities, we basically use the Golang's SQL interface modules to make sure that we can seamlessly interface the Golang-based socket APIs and the underlying C-based shared memory IOs. And the benefit of we choose to use a layer design is because we want to reduce the implementation effort and avoid re-implementing the entire stacks. And what we need to do, as you can see on this slide, when we switch from a kernel-based implementation to a shared memory-based implementation instead, we just need to replace the imported modules. So the net module is the default kernel-based HTTP networking module provided by Golang. And there's two programs I listed here as example, a socket server program and a socket client program. For the server program, what it needs to do is to refer to the modules and use its APIs to open a listener socket and use this listener socket to wait for the connections from the clients. And on the other hand, the clients can also refer to the net modules and use the dial calls to get connected to the servers. And after the connection is established, then the server can use the read call to receive the data, and the client can use the write call to send the data. And after all the data transfer is complete, then they can just close the connections. That is kernel-based implementations, but when we switch to a shared memory-based implementations, we don't need to refactor all of this code. What we need to do is to simply replace the imported modules from Golang's net modules to our XIO modules, which use the shared memory processings. Only involves 3 lines of change. And further, by import the socket APIs into the Golang's HTTP REST API and 3GPP API, we can keep most of the code unchanged and do the porting of the implementation from kernel-based solutions to our shared memory-based solutions seamlessly. And any questions so far? Okay. So here is about how we support the user sessions, concurrent user sessions in our 5G core by using a shared memory-based implementations. And we use the connections to distinguish different user sessions. Basically, you can consider each user session as a distinct connections. And before a pair of network functions, they can communicate with each other. They need to set up connections with each other by using these different API calls we provide. And the key that we turn the stateless processings into stateful processings is to have user session tables in our XIO stack. Basically, when the XIO stack receives a new data, it will do a table lookup by using the IP4 tuples to identify which user session this packet belongs to. And after it determines there's a user session that is ready to serve these data, then it will dispatch the data to the corresponding read queue of that user thread for it to process. And if there's a lookup miss, that means there's no connections between these two. And they need to follow the standard procedure to establish connections before they can send and receive data. So here's about the evaluations. Basically, we have 2 different setup of evaluations. The first is to use a commercial 3GPP compliant testbed that is built with real hardware. And for the user requirement of the mobile devices, we use the laptops and we equip each of these laptops with 5G dongles to convert that into mobile devices. And we also basically build a very small scale radio access network by using by purchase the radio unit and also the other radio access network components from different companies. And for our core network, we simply use the company servers and deploy all our softwareized 5G core on top of them. And for the commercial test bed, we mainly focus on two control plan events, which is the user registration and the PDU session establishment. But because we only have 5 5G dongles and we want to scale up, we don't have money to purchase the device. So we also have a workaround, basically use UE run simulators to scale up to more UEs. And for this setup, we additionally looking at the paging event or the idle to active transition event. For the alternatives, we compare our R25GC Plus with the free 5GCs, which is the platform we built on top of, but free 5GC use the kernel-based kernel-based networking for the control plan events, which is much slower than us, as you can see here. So this is the result we evaluate on top of the commercial test bed, and we try different UEs in this experiment. But overall, what we can observe is that for the UE registration event, our design is 1.5, can achieve 1.5 low latencies with a single UE, and 1.3 low latency when we increase to 5 UEs. And the same thing we can observe when we switch to a PDU session establishment event. We are much better and can achieve a latency improvement almost 2 times. And for the simulated setup, basically we can test it with more UEs. And we can see the same thing here. Basically for the UE registration event, we can achieve almost 2 times latency reductions. And this is the same for the PDU session establishment. And for the paging event, we can achieve around 1.6 times latency reductions compared to a kernel-based free 5GC implementation. So far, I discussed the system improvements we made to handle the penalties we discussed earlier. And what we can see is that our system implementations can reduce the control plan by almost half. But the question is this enough? And of course, it's not enough, because you may still remember how complex the entire control plan protocols looks like. But how can we improve that? And that is another benefit, I want to say, for jumping into software-based implementations, because this can make it much easier for us to reconstruct the protocols by improving our core network. And our early effort in the Kalinji paper or Kalinji work suggests that by carefully improve the protocol designs in the control plan, we can further reduce the control plan latencies by almost 2 times. So I may not have time to cover details, but I will briefly touch upon that. Sorry. Yeah. So I want to use our improvement of 2 control plan protocols. The first is the idle to active transitions. And the key idea is that by combining or remove some unnecessary protocols or protocol steps within our control plan protocols, we can reduce the number of messages by half compared to the 3GPP. This is exactly what we have for the idle to transition event. And for the handover event, do the same things. By carefully optimize the protocols, we can again reduce the message by half. And that means the entire latency we spend on completing these different control plan events can be further reduced by half. And plus, we can do a 2 times performance reduction by doing the system improvement. The total improvement we can get is almost 4. So here are the summaries. Basically, I want to summarize the lessons we learned for evolving to 6Gs. So we know that there's considerable interest to have an improved next generation of the cellular networks, especially to fulfill the demand of the emerging applications for high throughput and low latency access to internet services. And we see this trend or evolution of the control plan in the core network. They are becoming more software-based, and loosely coupled. This can give us lots of flexibilities and reduce the operational cost of the cellular providers. But the softwareizations and the adoption of the microservices, they come at a price. And the problem is that we often overlook the penalties that is in the control plans and its negative impact on the user plans. But does it mean the evolution is wrong? Basically, should we jump back or jump back from the softwareizations and microservices? Of course not. But instead, we need to think holistically of the protocol and the system implementations by going beyond just using improved software platforms. And by doing this way, we can still benefit from the softwareizations for its flexibilities, but also get much lower penalties or reduce the penalties for using these different optimizations. And we already open source the R25GC on GitHub, and here's the link. And I encourage you to try that. And if you have any questions or comments, feel free to email us on our Google Groups. So I probably conclude here, and I welcome the questions. Thanks.
We have time for questions. Okay. I understand that there's a lot of things covered here, so but still feel free to ask. The person who developed the system or who is part of the team that developed the system. Who owns this technology?
You mean the R25GC or?
L2, yeah, L2.
Yeah, it's part of the team, basically between the UC Riverside and also National Yangming General University.
So it's owned by two groups?
Yes. So we started this project 4 years ago, and we involved this faculty core for many generations already. And in the early generations of these 5G implementations, we have that issues I discussed earlier, basically the mismatch between the shared memory.
Can you use the mic?
Oh yeah, between the asynchronous shared memory and the upper layer synchronous 3GPP SPIs. And we found that problem. And because if we just directly use the shared memory APIs, the entire 5G core implementations is not scalable. It is stateless, so that we cannot scale to multiple concurrent user sessions. And the porting is actually a pain for, basically we need to do lots of code changes in the free 5GC when we move it to the R25GC. So that's why we need to improve our implementations and designs by having this R25GC Plus, so that we can resolve that mismatch and the conflicts and make sure we can directly use the network functions from the free 5GCs, but in the meantime, leverage the high performance data plans by using the shared memories and seamlessly integrate them together.
Has this been used by any company?
So the free 5G core, which is the one that we built on top of, has already been used by many companies. But the one that we are developing, we are still trying to sell in that.
Is this been patented?
No. It's not in patent. And luckily we use the Apache license 2.0, so anyone can get the code online and free to modify that. So that's why the free 5GC is much more popular than any of these other platforms.
You say that this is the first ever work to try to use software to
yes, starting from the free 5GCs.
Run network services. Right?
Yeah.
So who started this thing?
By the Professor Jesse Chen from the NYCU. So he started that project several years ago, and later he invited us to join the team to develop a high-performance version of the 5G core scheme.
So the origin idea was from the so-called Yangming University.
Yeah, right.
Okay.
So they have a huge army that they can devote effort to develop large-scale 5G core solutions. That is called free 5GCs.
Questions? Yes?
Thanks for your very insightful talk. I'm not working purely in this project, this field, but I have some comments, and it might make sense or not make sense. So one thing I'm thinking, like the software-defined infrastructures basically is trying to separate the data plane to the from the control plane. So like our traditional router-based computer networks, our like the traditional routers actually it has some intelligence. It's not like you know the fully implemented computer, but it do have some intelligence.
Yeah.
And later on, we have this software-defined networking. It separates totally the data plane and the control plane in order to have a more flexible management functions. But now it seems like the problems you are presenting, like because of this separation, and when there are some events triggered, when we need to change to manage or to management this system, and it results in this pretty high overhead, the communication overhead and also the traffic overhead for the management functions. And one solution you have proposed here is to use the shared memory between the data users instead of like going through back and forth between the centralized controller to the user device, right? So I'm thinking, have you ever thought about, for example, perhaps one solution it could be like have some predictive agents and to predict what kind of events is going to happen in the next, you know, like short term.
Yeah.
So in that case, and perhaps you can take the actions before rather than when the events, you know, come. So and also develop some other mechanisms, you know, to reduce this communication cost. And then the second thing I'm thinking is it possible, like, to build this kind of event-driven autonomous, let's say, the decision-making systems instead of like you have this centralized, but you decentralize the system and to have this, for example, the let's say you have a small scale, and then you can make the autonomous decision rather than have that, let's say, this centralized control.
Okay, so for your first questions, I mean, a typical example of that application is the mobility predictions. Basically, we are moving from different cell sites, and basically we can predict the user mobility behavior, and we move the user data from one radio access network or one cell site to the others, so that they can basically have a much shorter data state transitions when it involves with the core network. So I mean, for our first question, that is possible, and we look into that, but we haven't done anything on that aspect so far. And for the second problem, I mean, it is possible to deploy or break down our core network in a distributed manners. Basically, put some of the part of the core network to the edge. For example, for some components, like I showed earlier in the core network, like the AMF and SMF, there's already some practice that they try to deploy these functions at the edge cloud because they are more frequently to be accessed. But for the other less frequently accessed functions like the UDM, UDR, they choose to put into a centralized data centers to amortize the deployment cost. So I mean, your idea is of course feasible and practical. And I mean, although they're still basically underexplored, we haven't looked into this part a lot so far.
Yeah, because in the software-defined networking, the data plane is has no like intelligence at all. It's just a receive and forwarding, right? If we can like add maybe some intelligence to the close to the end users, and perhaps it can, you know, improve the performance of the network and also reduce the latency of the communication.
Yes.
I don't understand very well of, you know, every details of the, you know, the solutions you proposed, but I'm just thinking in a very abstract level, like.
Yeah, I mean, your idea is basically very complementary to all of these organizations. Basically, our focus is, because we want to use the softwareizations and the microservice-based deployment paradigm to reduce the operational cost of the core network. But because people, before they don't know, such transition in the core network, or especially in the control plane, can have some negative impact in the user plans. But we still want to retain the flexibilities for the use of softwareizations, but in the meantime reduce its penalties for using it. And that is our key considerations in this work. But of course, there are many other aspects we can consider in the future, like doing a better mobility predictions, and also by considering how should we optimize our deployment of the core network by making it more distributed and close to our users.
Yeah, there is this trade-off.
Yeah, right.
Yeah.
Okay,
Thank you very much.
James.
Let me give you this mic here. Okay. So that everybody can hear.
So, can you? So, what are the security implications for having a shared memory storage?
Of course, there are some security issues. Basically, if you put different functions, they are not trust each others, and let them use the shared memory, there will be some security concerns. But that depends on how the operators, when they deploy these network functions using shared memory, they need to define their trust models. If the operator think, okay, all the functions that use the shared memory, they should trust each others, then the security is less of concern. Because it's not like the public workload. Your workload may exist with any other like cloud workload in the same data centers. For the deployment of Cellular core, that is quite different. That is more like on-premise manner. So you have a dedicated machine that ran from the cloud.
So it's vulnerable if there was a vulnerability in the trusted sources. Okay.
Yes, but I couldn't see that for the in the Cellular network. But if we are discussing a general cloud workload, yes, that is definitely the issue.
Our time is up, so if you still have questions, you can talk to the speaker, during the pizza time. All right. Thank you very, very much.
Thank you very much.